Hello friends, in this video we are going to discuss about Cauchy's integral theorem. So before we start, please subscribe the channel and hit the thumbs up button. Also hit the bell icon so that you get notified when new video will be uploaded. Right, and share with your friends. Help me to grow my channel, inspire me to create new contents for you. Okay, if you want to follow me on Insta, then you can follow me OZHALAKHYZZIT 123. This is my Insta ID. You can follow me there. Okay, so now let's start. So according to this theorem, so before you start watching this video, please make sure that you have watched all the previous lectures. Links are given in the description box. You may go through. Okay, then you will understand better. Okay, so now suppose we have a function. Let me just rearrange this. Okay, so suppose we have a function. If a function, let me take the black color. Okay, if a function f of z is analytic and its derivative f dash of z continuous at all points inside and on a simple curve C, then integration of f of z dz along C is equal to 0. Okay, so this is equal to 0 where z is a complex number. Z is a complex number. Just wait. Z is a complex number. So suppose we have a region enclosed by the curve C, suppose, and if the fz is analytic within this region, that means all points inside the region, inside the curve, and at all the points on the curve as well, then and also the derivative of this function is also continuous at all the points and inside the circle and on the curve, inside the curve and on the curve, then integral of f of z along C, that must be equal to 0, right? So hope you have understood this. So now let me clean this. Okay, so let's prove this one. So how to prove this? So let us consider a function. Let f of z, let me take this one. Okay, just wait. Let us consider that a function f of z be analytic and continuous, and and f dash of z continuous in the region R in the region R enclosed by a simple curve C, and also on the curve C, so it is analytic and derivative in the region R enclosed by a simple curve in the region R enclosed by a simple curve C, and on the curve C. Okay, here this function f of z is suppose u plus iv, and z is equal to suppose x plus iy, which is a complex number. Right, then let me scroll down the page. So now you see what we are to show, we are to prove that integration along C f of z dz is equal to 0. We need to prove this one, right? We have to prove this. Okay, this is equal to 0. Now, so if z is equal to x plus iy, then dz must be dx plus I dy. So now integration along C f of z dz, it can be written as integration along C f of z is u plus iv, and dz is nothing but this, right? So dx plus I dy. Now let us multiply these two. So what we're gonna have, let me use another ink here, u plus iv into dx plus I dy. So if we multiply u dx, then u I dy, then iv into dx, then iv into I dy, that's going to be minus 1 into v into dy. That's what we're going to have, right? Now we can write du dx minus dv dy as a real part, and taking I common from these two terms. Let us take I common from these two terms. Then what we're going to have, complex part, I u dy plus v dx. That is what we're going to have. So here we can write integration C du dx minus v dy. We can separate the real and integral, real and imaginary part this way. Then let me write this one first. Okay, just v dx, then u dy plus u dy. So this I is written here, this is the I outside the integral, right? So now here you see, let me scroll down the page. Okay, so we need to show this thing is equal to 0, right? So now what we can do here, we're going to apply the Green's theorem. Okay, so what was the Green's theorem? So integration of phi dx plus psi dy along C is equal to double integration in the region enclosed by the curve C is equal to first take psi, which is with dy, partial derivative of psi with respect to x. Then we need to take the minus of phi, and which is with dx, that should be differential, the first partial derivative of phi with respect to y, and dx dy. That is the theorem, right? This is dx dy, so hope you can recognize this. Let me write this one properly. This is dx dy, right? So if we apply that, here we have to consider u as a phi. Then you can imagine this one as plus minus b, right? Plus minus b dy, right? So in that case, this minus b should be considered as psi. Then apply this Green's theorem. Okay, then what we're gonna have? So we're gonna have double integration r, instead of phi we're going to have minus b, so minus del v by del x here, then minus, instead of phi we're going to have u here, so del u by del y, then dx dy, that's what we're going to have. So again here also we're going to apply the Green's theorem, considering this one as phi and this one as psi, and if we do so, then what we're going to have, integration within r, we're going to have del u by del x minus del v by del y dx dy. That's what we are going to have. So here you see what we have done. Let me clean this. So we have applied the Green's theorem by Green's theorem. By Green's theorem. So hope you have understood this. So now, as we have already considered that f of z is analytic, so it must satisfy the CR condition. By CR condition, that means Cauchy-Riemann conditions. So let me scroll down the page. So here you see, just wait, this is f of z along C. So let me take this as equation number 1. Now let me scroll down the page. Okay, so here you see, as we have already considered that this function, you can see this function, this is analytic, right? So that's why it must satisfy the CR condition, Cauchy-Riemann condition, that we have already discussed earlier in earlier lectures. Okay, so by CR condition, so what are the two conditions? Those are del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. Now let us take this as equation number 2. Now let us use this equation number 2 in equation number 1. Then here we can replace this minus del v by del x by del u by del y. Okay, so it will be replaced by del u by del y, then it will be cancelled by this one, right? So it's going to be 0. So we can write that using equation number 2 in 1, what we're going to have on the left hand side, we're going to have the same thing, that integration of f of z along C, integration r. So as I have already told, this is replaced by del u by del x from this equation, minus again sorry, not del u by del x, del u by del y, right? This is del u by del y. So minus again you have del u by del y dx dy. Then next part, here you can see this is del u by del x, it can be replaced by del v by del y right here, then it will be cancelled by this one, then it's going to be 0, right? So if we replace that, then what we're going to have, plus I integration del u by del x is replaced by del v by del y, then again we have minus del v by del y minus del v by del y, then dx dy. So here we can write dy dx dy. Okay, so now let me scroll down the page. Okay, so here you can see these two days to gone, these two also gone, so we have 0. So integration f of z dz along c is equal to now 0 plus I into 0, which is nothing but 0. That is what we needed to prove, right? So simply we can write integration f of z along c is 0. That is what we needed to prove, hence proved. This is the Cauchy's integral theorem. Right. Now let us discuss about the extension of Cauchy's theorem to multiple connected region. Okay. So what we're going to do, extension of, let us discuss about extension of Cauchy's integral theorem to multiple connected region. So what is the theorem, right, for multiple connected region? So let us discuss that. Now you see, if f of z, which is function of z, is analytic in the region R between two simple closed curves C1 and C2, then integration of f of z dz along C1 is equal to integration of f of z dz along C2. That is the theorem, where z is complex number, right? It will be better if you write, instead of number, if you write complex variable. Okay, so is a complex variable. So here also in the first one, here also let me mention here, let me write here a complex variable. This is a complex variable. Okay, complex variable. Here also in integral theorem, let me write here complex variable. Okay, it will be better now. So now you see, so now let us prove this one first. Okay, so proof. So here you see, so we know that by Cauchy's integral theorem that f of z, f of z, just wait, dz is equal to 0, right? So as we have considered considered a region enclosed by two simple curves, one is C1 and another is C2. Okay, another is C2. We have considered that way. Now you see, here, so this f of z is analytic within this region, right, within this region bounded by c1 and c2. So this can be converted. Let me scroll down the page. This can be converted into, simple connected region. This is multiple connected region. It can be converted into simple connected region, so giving here cuts. Okay, so giving cuts here. This is okay. Now this is c2, this is c1, so I have given cuts here, right? So this is the direction I have taken. This is A, this is B, then again clockwise along C2, then this is BA, this direction is BA, right? So this direction is opposite to this one, right? So if this is AB, then this is BA, this direction is BA, so we have taken that way. So now here you see where the path of integration is along, where the path of integration is along AB and the curve C2 in clockwise direction, in C2 in clockwise direction, as shown in this figure, and along BA, this is BA, as this is AB, so this must be BA, along BA and C1 and along C1 in anti-clockwise direction, in anti-clockwise direction, right? So that means we can write this one as integration along AB f of z dz plus integration along C2 f of z dz plus integration along BA f of z dz, then plus integration along C1 f of z dz is equal to 0. So this is split into 4 parts, right? So now let me scroll down. Okay, here you see that these two are opposite, since, just wait, since here you see integration along AB f of z dz is equal to minus AB. This BA can be written as minus AB, right? So just wait, you can write, let me write, okay, you can write that way also. Integration BA f of z dz is equal to minus, if you take here minus sign, then it's gonna be AB f of z dz, right? So that's why let us replace this by this one. Okay, then what we're gonna have, integration along AB f of z dz plus C2 f of z dz. Now let us make it minus, then it's gonna be AB, this B are gonna be AB on making minus, on making it negative, this B are gonna be AB, C1 f of z dz is equal to 0. So here you see these two are cancelled. Now let me scroll down the page. So what we have got, C2 f of z dz plus, this was supposed to be C1, f of z dz here along C1 is equal to 0. So just wait, let me write it properly. This is C2, this is C1. Okay, so now you see, let me draw the diagram again. I have considered this way, that so I have taken given cards here, right? Let me draw the diagram again. This is C2 and this is C1. This was in anti-clockwise direction. This C2 was in clockwise direction. So this is AB, this is BA, right? AB, this is BA. So if you reverse the direction of C2, then this positive will be negative. Just let me write this one first this way. Let me keep the integral along C1 on this left hand side, dz. Now let me shift this one to other side, minus C2 f of z dz. Now if you reverse this direction, if you take the opposite direction, then this minus is going to be plus. Okay, so how to do that? So just what we have to write here, that reversing the direction of C2, we get, let me scroll down, integration f of z dz along C1 is equal to, then if you reverse the direction, then this minus will be plus f of z dz along C2. That is what we needed to prove. Okay, so that is what we needed to prove. This one here you can see, right? This is the theorem. So hope you have understood this. So in the next video we're gonna discuss another topic, right? So hope you have understood what we have done. So in the next topic we're gonna discuss about Cauchy integral formula. Cauchy integral formula, not Cauchy integral theorem. We have already discussed Cauchy integral theorem. Next we're gonna discuss about Cauchy integral formula for the derivative of analytic function. Okay, then we're going to solve problems also related to this topic. Okay, so see you in the next video.